Let's take a look at a design example. So what we want to do here is to design a full wave rectifier that's going to produce a peak output of 12 volts while delivering 120 milliamps to the load and keeping the ripple voltage to 5% of that nominal 12 volt output. We're told that we have an input available that's 120 volt RMS at a frequency of 60 hertz. And so we're going to assume that this is just the voltage that's available at an outlet. So we can say we're going to assume that this is a sinusoidal input voltage. Okay, again, as always, I would encourage you all to pause the video and try to work through this by yourself before coming back and watching the video to see the answer. So we have several things we need to determine. First of all, we need to determine which type of full wave rectifier we want to use. So remember we talked about two different types, center tapped versus full bridge rectifier. And so I'm going to choose to use a bridge rectifier here, but we could also use a center tap transformer rectifier if we wanted to go that route. So now that we know we're using a bridge rectifier, what do we need to figure out in order to meet the specifications in this design example? Well, a couple of things that we need is we need to know our diode specifications, because we essentially already know our circuit layout, so we don't necessarily need to know any of that. But we do need to know how basically hardy our diodes need to be, and we also need to know what type of transformer we need. So we need our transformer specs, or we need to know what type of transformer to put in the circuit. So those are kind of the two things that we're targeting, and I guess one other thing as well related to our ripple voltage is we also need to know our capacitor size. Okay, so let's first look at finding the specifications for our transformer. So for our transformer, what we can say is we know that our Vs max is going to equal to our output max plus 2 times our V gamma. So why 2 times the V gamma? Let me just copy a figure from one of our previous videos. So this is showing for the case of our Vs greater than 2 V gamma. So 2 of the 4 diodes in our bridge rectifier are forward biased. So this would be our V out here. And so we can see that when we have a maximum V out, this equation here would be true. So our Vs max is equal to V out plus 2 V gamma. So we could do KVL around that loop. So plugging in values, of course, for this case, we have a nominal output voltage of 12. That's our maximum voltage, plus 2 times our V gamma. We weren't given a V gamma, so let's just assume a typical value. So it's always good to state our assumptions. So let's say assume V gamma is 0.7. Again, that's a typical value for silicon p-n junction diodes. So 2 times the 0.7 for our V gamma, and we get that that is 13.4 volts. So basically we want 13.4 volts on our secondary side. We know we have that 120 RMS at 60 hertz available on our primary side. So the first thing that we want to do is we want to convert this Vx max to a Vs RMS. So Vs RMS is equal to that maximum value of 13.4 divided by square root of 2. And again, this is because we've assumed it's a sinusoidal signal. If you have different types of signals, square wave, triangle wave, that RMS equation won't be the same. So plugging that in, we get that that is 9.48 volts approximately. Okay, so now with that information, we know we want 9.48 on our secondary side when we have 120 RMS on our primary side, so we can figure out our turns ratio for the transformer. So we can say N1 over N2 is equal to V1 over V2, where 1 is the primary side, 2 is the secondary side, and in this case we have 120 volts RMS on our primary side, and we know based on our desired output voltage we need 9.48 volts RMS on our secondary side, which gives us approximately 12.66 as our turns ratio. So that would be the ratio we would want in our transformer. So now let's take a look at meeting our ripple requirement. So remember we wanted to keep the ripple to 5% of our output voltage. And so we're going to do that by selecting the appropriately sized capacitor. So we want 5% ripple. So first of all, let's figure out what that value is. So that means we want V ripple to be 5%, so 0.05 times our Vm, where our Vm is 12, so times 12 volts, and we get that that is 0.6 volts. So now what we're going to do is rearrange the equation from a previous video where we talked about filtering and our ripple voltage, and we can solve that for our capacitance. So we know that C is equal to Vm divided by R times VR times F ripple. Okay, well, we can figure out what F ripple is, because remember, for a full wave rectifier, F ripple is going to be twice the input frequency, and in this case our input frequency is the 60 hertz. We also know our Vm, that's our 12 here. We know our V ripple, that's sort of what we were designing for, but nowhere in here do we have any mention of an R value. So what do we do about this R value? Well, of course, what we can do is we can use Ohm's law. And so we can use that in one of a couple different ways. We can say, well, we know that our Vm is equal to the load current times the load resistor. And that's what this R is up here. This is our load resistor. So with that, we could explicitly solve for our R, or we could just say from this equation, we know that Vm over R is equal to that load current. And right here we have Vm over R. So we can go ahead and rewrite this and say this is just IL divided by VR. And now remember, I had said that our F ripple is actually 2 times Fn because we have a full wave rectifier. So from there we plug in values. So our IL was 120 milliamps, so I'm going to change that to amps. So we have 0.12 amps. Our VR is 0.6 volts. We have a 2 times our input frequency of 60 hertz. And so if we plug all that in, we get that our necessary capacitance for our desired ripple is 1.6 repeating millifarads. And so of course, if depending on how important it is we keep that ripple below 5%, we can make that capacitance a little larger. So basically, if we're saying our ripple is less than 5%, then our capacitor would need to be greater than or equal to 1.6 millifarads. So because we're going to need R a little bit later on, let's go ahead and revisit this right here and say do what I was talking about earlier and say we can go ahead and solve for this R explicitly. We know that's Vm over IL. So plugging in, we have 12 volts for Vm, 0.12 amps for IL, and that's equal to 100 ohms. So now we could have just plugged that 100 ohms into this equation. That would have been fine, but we didn't necessarily need to. However, for the last thing that we're trying to find, so we've done our capacitor size, we've done our transformer specs, now we need to look at our diode specs. And so we're going to use those two equations that we didn't derive, but we just put up for our maximum and average diode current. And both of those equations require us to have this R value here. So first of all, let's calculate our peak diode current, ID peak. So this is going to be equal to our Vm divided by R times 1 plus pi times the square root of 2 times Vm divided by VR. So plugging all of that in, we get approximately 2.50 amps. So the other thing that we want to consider is our average diode current. So ID average. So the equation for that, again, we're just going to plug straight in. So we had 1 over pi times the square root of 2 times VR divided by Vm times Vm over R times the quantity of 1 plus pi over 2 times the square root of 2 Vm divided by VR. Plugging all of that in, we get approximately 0.132. If you left everything in volts, ohms, This will be amps, and of course we can write that as 132 milliamps as well. Okay, so one other important thing we want to know about our diodes is the peak inverse voltage. Right? We need to know how much voltage it needs to be able to sustain and reverse without breaking down. And so for that, let's again look at our circuit that we had previously. So this is the case when D1 and D2 are forward biased. And so of course we had D3 and D4 here, which are reverse biased. And so the polarity of these, remember we had defined sort of a VR previously. So our diode D3 looks like this, which means for our VR, the positive is going to be on the upper side of that. So we have something that looks like this. So this would be our VR, which is equal to our peak inverse voltage if we have a positive value for that. So what we can do is KVL to figure that out. So we can say VR is equal to, and then we have our VS minus V gamma, and then we're back where we started to. So what we can say then is that our PIV, our peak inverse voltage, is equal to the maximum value of VS, because of course we want this to be as high as possible, minus V gamma. So that is 13.4, because remember we had found that this maximum value corresponding to our desired 12 volt output was 13.4 on that secondary side of the transformer. So we have 13.4 minus our assumed V gamma of 0.7, which gives us 12.7 volts. Okay, so what we would need to do then is we would need to take these diode specs, these three boxed items you see on the screen, and we would need a diode that can meet these at a minimum. So for instance, if we consider our peak current, our diode should be able to handle not sustained current, but momentary currents up to, let's say, 3 amps to be safe. We wouldn't necessarily want to over-design it too much. We wouldn't need a diode that can sustain 10 amps of current, because then we're paying too much for sort of a quality that we don't need. So it's sort of a fine line to balance there. The other things to note too is that this transformer turns ratio that we found earlier, this 12.66, isn't necessarily standard. So what we would need to do is weigh the benefit of having a custom-made transformer with something close to this turns ratio, or maybe trying to adjust our design a little bit so we can use something that is more standard. Another thing to keep in mind too is that this input voltage of 120 isn't necessarily always going to stay constant. So the voltage available at the outlets in your house, for instance, can fluctuate as much as 10%. So all of these things I'm just mentioning just so you're aware that, of course, problems in the real world aren't quite as simple as sort of these textbook problems. And this problem that we looked at right here is a little bit simpler because we're just getting used to this material. But there are other considerations that you would need to consider that are sort of out of the scope of what we're looking at right now.